Hi everyone, thank you for coming. My name is Lars Albertsson. I run a small little data engineering startup called Skling, and I should tell you what it does in a minute. Some of you might have seen a graph that looks like this. I've seen a couple of those when working with data, and they tend to freak people out, in particular if they co-occur with like an important launch of some kind, like a new country or on a marketing campaign or something. Afterwards, you can see that this does probably not reflect reality and what happened, but while you're in that bump, people get very anxious. You might also have seen graphs that look like this. There's a mysterious dip, like every once in a while. We had it for a reporting application at some point, and things dipped at midnight. It took us a long time to figure out why. Or like this, mysterious bump in the middle of the night. Where does that one come from? Or like this. This was a case where we had users that were on the free tier, and they were using, for some reason, premium services. That was supposed to be 0, but it reset at midnight every time. These are all examples of mishandling of time in data processing, where the graphs don't reflect reality, but somehow we goof up when handling with time. So I will show you some like patterns, nanny patterns that I have learned during the years, and share a handful of the tools from the toolbox that I have in dealing with time. The context for this presentation is so-called big data processing systems. Now that's a buzzword on the fading, I know. But I'd like to point out that you might associate big data with like scalable technology and Hadoop and things like this. Well, Hadoop and Kafka were the enabling technologies from an economical standpoint. They made it possible to collect all the data that you have in one place. Not technically that was possible before, but it was economically feasible suddenly. And the big difference in working with big data patterns and workflows is not that you can do things like machine learning. The major difference is that you can share your data and democratize it within your organization. And that's actually the real value of big data. What typically happens when you sort of transform into big data workflows is that you, instead of doing the usual point-to-point integration where you go and speak to all of other teams and get data from the systems, you ask them to dump their data into the data lake, or you do it for them. And the first time you do that, that's not so great. But with time, more and more data ends up in the data lake. And after a while, people see that, oh, there's value in having this as real time as well, so they might install something like Kafka. So the context of this presentation is an environment where you use these types of data lake or stream processing environments. And this is also what our startup does. We do these things as a service, offline data processing. And the purpose is to enable all sorts of companies, not just the very leading edge of tech companies to get all of this value. And we have a very simple marketing strategy. We go out and share the knowledge that we have promiscuously without anything in return. And now that you've seen this marketing slide, I'll share the knowledge, and I hope you find that a reasonable deal. A data platform typically looks something like this. This includes the picture includes batch processing only. And I'd like to highlight one component here to the lower right. And it's a component called the workflow orchestrator. The workflow orchestrator is the data equivalent of a build system for source code. It knows the dependency graph between things, and it knows how the raw data is supposed to be transformed through multiple steps into refined data. So from web clicks to reports or recommendation indexes and so forth. And these transforms form pipelines. There are two decent workflow orchestrators out there that I recommend. One called Luigi from Spotify and one called Airflow from Airbnb. How many people feel that they are familiar with what an environment like this looks like? Okay, I see like a hand or two. last time I held this presentation, everybody raised their hand. So I'll try to adapt accordingly and maybe slow down a bit when I explain some concepts, and maybe we'll have to skip some slides in the end. From a data processing perspective, we can divide data that we have into different categories, or from a time perspective, we can divide it into different categories. There are facts, also called events, something that happened at a particular time, and it's time-stamped by some clock out there. And you get a continuous stream of events, typically. There is also state, like the users in your database or what you currently have in stock. This is usually, the source of truth here is usually databases that hold the current state, which you do not query from these big data structures. You instead dump the contents to the data lake on a regular basis, like daily or something. And then we have claims, where we state something about the past. Like, in March, we believe that these users were fraudulent. So, looking at those facts and how they progress through the system, we can see that we have different times. We have the event time. This is the time that the thing actually happened. And then event is sent to the backend, and we get a registration time, which is when we first see the event. And then it goes through our own network to be ingested into the data lake, so there's an ingest time. And later we process it if we're doing batch, that's a processing time. And then we also have the domain time, which only occurs if we have claims, like the fraudulent users of March. These are different time scopes. Sometimes they're the same, sometimes not. We also have clocks in these systems. And clocks, I don't know if anybody attended the How Shit Works time presentations, but clocks, as stated there, don't measure what time it is. They measure the elapsed time. And first you have to tell them one way or another what time it is. Usually that works, sometimes not. They are of different quality. And sometimes some of them you control, some of them you don't control. In your sort of modern backend, you can typically control the clocks. They are of good quality, and you set them to UTC. If you have legacy systems, they're usually good, but they might be set to something else. And the client clocks you have very little control over. Clock time is, for us humans, it's divided into calendars. And if you take a naive look at the calendar, it kind of looks something like this. It's a fairly mathematical definition. Now, with that naive mathematical definition, these properties would seem to hold. Like a day is a certain number of seconds. If you go past n years, you can bump the year number by n. If you go forward 364 days, you might end up from the beginning of the year. You might think that you end up in December. If you go forward 60 minutes, you might think that you forward an hour, and so forth. Now, if you can find counterexamples to these properties, please raise your hand with the number of fingers indicating how many counterexamples that you find. There's one counterexample for each of them. We have 3 over there. Any higher bidders? 2 over there. Yeah, the number is usually between 1 to 4 when I ask people. Some of them are obvious or common. The first one is that we can have leap seconds. The year 0 doesn't exist in the social calendar. There's an astronomical calendar where it does exist. There was a switch to the Gregorian calendar, and that switch itself stretched on over centuries. So if you compare different dates in history in different countries, you might end up doing the wrong things. Daylight saving times, everybody knows. Time zones are a mess. You'd think that there are 24 of them, and that they are on hours. They are not. And some countries keep hopping back and forth over the date line. So they like skip a day, or they have 2 copies of the same day. And Sweden is very proud to be the only country that has the February 30th in 1 year, due to some mishaps with a switch from Julian to Gregorian calendar. Fortunately, these are unlikely to cause you trouble, right? Except for a couple of leap seconds actually cause a bit of trouble sometimes. I think there was an incident recently or the other year. The cloud providers tend to have a nice solution, at least Google. They smear out the leap second so nobody's supposed to notice. Daylight savings time, however, is bound to cause you trouble at some point. And my point here is that the calendars are not a mathematical thing, it's a political thing. It's politically decided. And the mathematical notion that you have in your code is an approximation of the political definition. So daylight savings time, it actually kills people. I'm not sure if you were aware. There are an elevated number of heart attacks when you cut off an hour, and it's not compensated by the extra hour that you get to sleep. And it also causes bumps in your analytics like this. Not much to do about it. You just have to sort of accept that and be aware. And this popped up just the other day just to illustrate how common it is to goof up with daylight savings time. This tweet is like 2 days old, where a company called New Relic, I'm not so familiar with the product, but they had two dates, November 3rd in a row, probably for goofing up with daylight savings time. Now, it can cause trouble in technical systems as well. This little code here, this is workflow orchestration code on the right. It implements a simple structure where you have, from a legacy system, you upload files, and then you take those files from what's called the loading dock, and you dump them into the data lake, and you change the semantics a bit to sort of match the conventions in the data lake. This is a very common pattern. Typically, the source system and their administrators are in control of the format of the upload and so forth. And it happened to me recently that we ran into trouble here. You don't have to understand the details, just leave with my explanation. Because the source systems were running on a local time zone with daylight savings, but I don't know if you see it, but the file names here and the structure is based on time. So what happens when spring comes, there's suddenly 1 hour missing and the ingestion will halt. Even worse, when autumn comes, you will get 2 data sets in the same hour, and if your systems are not aware, you will get some kind of silent data corruption there. So this is one example of how the daylight savings time goof up technical systems. It's common to, as I mentioned before, to use snapshots of databases. So if you have events that happen out there, the events on web or orders in your web shop and so forth, you typically want to add demographic information. So you take the stream of events that have been dumped to the lake and you join them with the dump of the user database, for example, to form a enriched event. Now, the dumps typically happen like at midnight, like once a day. And the events, they don't happen at midnight, because that's not when people shop. So you will join an event with a dump from a different time, either back in time or forwards in time, typically back in time. Which means that you will always have a mismatch. And the state of this user might not be the state that you have dumped from your database. You can usually live with this. Usually, if you try to cure this, the cure might be worse than the disease, but you need to be aware. And you preferably only want this in one direction. And this is the cause for this graph. Right? Some users are on the free tier, and they wake up in the morning and say, oh, I want to go premium today. And so they buy the premium thing, but according to the database dump, they're on the free tier. But they use premium services. And quite often the dump doesn't happen exactly at midnight, a few hours back or forth. So you might have a misaligned with the daily partitioning of your events that come in with the partitioning of the dump windows, which may lead to time mismatch in both directions. Again, probably not want to cure this, but you need to be aware. So there is a sort of philosophical or religious concept called event sourcing, which says that if we have, basically, if we have state in databases and regard that as a source of truth, we have lost information because we don't have the history and we don't have all the nitty-gritty details. So instead, we regard the endless append-only log of events as the source of truth. And if we need a database, or we can build a cached view by aggregating this source of log of events. This allows us to get all the details and do the joining to match the events that come in precisely at the same time. Unfortunately, there's also a cost here if you do, and it's much more difficult to do accurately in a batch join than just joining with a dump of a database. So people tend not to do this. All right. Now, some of you might think that, wait a minute, I heard that it's popular to do real-time processing and do stream processing instead. That seems like it would sort of solve this problem, because in the stream processing context, we might continuously update the view of our users by sucking in all the user events and then process them and sort of publish new things in the database. And that's easy to code, and in a way it's more elegant, but it turns out not to be quite that simple in practice. First of all, there is a significantly higher cost in operating stream processing environment than batch processing environment, so most people tend to gravitate mostly towards batch. And also, in order for this to be accurate, you need to have these streams of events and user changes synchronized, right? Otherwise, one might get before the other, and you can perhaps get the event of the user buying something before the user has even been created, and so forth. And keeping streams in sync is not easy. In stream processing, you usually have to choose windows over something if you want to do something interesting. Just processing one event at a time is not so fun. So if you're aggregating things, then you might choose to look at windows that slide carefully, or that overlap over time, or windows that don't overlap, they're called tumbling windows. And if you want to combine and join streams, you typically have a window over one stream and window over the other, and then join events from them. The canonical example here is impressions and click-through rate. So if you show ads, for example, you're interested in, for the ad that you show, within the next 15 seconds, how many people clicked on that ad. Then you have two streams and want to join them over a window of time. Whenever you have windows in stream processing, you need to choose what you window over. That choice is not easy. So, and there are different trade-offs. You can window over the number of events, which will limit the number of resources that you use to a fixed set. But it's often not so interesting from a domain perspective, because if you get a spike in traffic, that window will go down in time, so you might not have 15 seconds anymore for your click-through rates and so forth. So you might use event time instead, but event time, on the other hand, those are tagged with unpredictable clocks from the clients out there. So suddenly, if somebody has set the time wrong on their clock, you might get an event like 3 hours in the future, and that will suddenly smash your window to 0. So you might use your backend time instead, like registration or processing time, and then you have trade-off in between. I don't have an answer here. My point is that every time you do something in the stream processing with Windows, you have a trade-off, and you need to choose that very carefully. Stream processing is fairly complex. So back to batch, which is usually the easier choice. There are some pitfalls when dealing with event and batch processing related to time. One of them is with events that come in, in order to batch, we lump many events together, typically by a time, by the hour, or 15 minutes or something. And then we have to decide, is the hour done? Do we have all of the events from this hour? This is an example from Spotify, age 2013, approximately. We were collecting events by looking at all of the backend gateway hosts, and we were essentially doing for all hosts SSH into the host and copy the syslog file. This is a very arcane way to collect events, but it worked. It worked for a while, because the more hosts we got, the higher likelihood that some host would be down and we wouldn't get the events. So we had this question, when are we done? When should we start processing? When should we give up? And we tried to tweak the system, but it just didn't want to behave. So eventually we went to a Kafka-based solution. And that at least got the events in. But now you can have late events, in particular if you have mobile clients. You never know sort of the upper boundary of how late your events can be. So you have to decide, when is the hour done? When can we start processing this hour? So one very technical Swedish company, they decided on the strategy that we look at the clock, the hour is done, we start processing right away. And then if we get more events, when this more has reached like 1%, 2%, we do reprocessing downstream. This is a bad idea and an anti-pattern, because then you have prematurely decided your trade-off point for everything downstream. And that may or may not be appropriate for the consumers. If you are doing financial reporting, for example, it might very well be inappropriate. There are some tools out there that do support reprocessing or some concepts. Sorry, I'm trying to get rid of this thingy over here, but it doesn't go away. The most well-known one is Apache Beam and Google Cloud Dataflow, where they have built-in support to explicitly handle late incoming events. That, on the other hand, makes the processing or programming interface more complex, and you effectively move to from an operational standpoint, move to a stream-based system, which has a significant cost. There are some other ideas, like keeping track of what data sets were used upstream for the things you built downstream, and then look at them and see if they're good enough. But there is currently no really good tooling here. So I try to avoid this solution. If we look at the event collection again and getting the data in, the time to use when bucketing data in buckets and deciding whether to reprocess or not should not be event time, not registration time, but ingest time, something close, very close to the destination. Because then you know that there's very little risk that anything comes late according to that timestamp. So what you typically do is you take all of the events that come during an hour and you throw them down into data sets in a data lake. The data sets are represented by directories where you pull in a bunch of files, and then once the hour is done, you set a marker file, which by convention is named _success, and indicating that this data set is now done. It can be processed downstream, and from that point on, you should never add anything to the data set. It's immutable. So, but you have to downstream decide if data is late for some reason, according to event time or registration time, what do you do? And that depends on your use case. In the bump example, you have to decide for this particular use case, what do my dashboards or my applications want to see? Do they want to see the drop, or do they want to see that the data from this time period is not here yet? Those are the choices that you have. This is some code to explain how you do the latter, how you sort of recover from data coming late and get more accurate even though the data is late. The code on the left is workflow orchestration, and in the definition of the dependencies for this job that require there in bold, you say that for this particular hour, the events that I care about, I will not only look at the ones that are ingested this hour, I will also look into the future to see if anything is coming late. And this will delay your processing. You wait for late coming events, and you accept that delay to get better quality. And the code on the right is how the corresponding Spark code might look, where you take 1 hour at a time and you throw the other events out, and you only care about this particular hour. And then you validate your assumption by counting the number of events that fall outside this window that you assumed. And you keep track of that, monitor and track that number. So beforehand, you don't know how long you should wait, but afterwards, you will know if you have waited long enough. And downstream consumers will have different requirements on whether they want the data fast or whether they want accurate data. For dashboards, insights, and so forth, you usually want fast data. For financial reporting, etc., you care more about the quality, and you are prepared to wait for a long time. This is not, if you have the right workflow orchestration, this is not a non-overhead, not a problem. You just have a different parameters, and you run several jobs in parallel, and the DAGs for your processing will look different as displayed on the right. It might also happen that you get additional information later that you want to care about. So again, at Spotify, we were doing reporting. We later got this extra data set of albums that were decided to be fraudulent, and those should be disregarded from the financial reporting and from the royalties payments. And that's sort of treated similarly. You do fast incorrect one, and you do later one with higher quality. Sometimes the thing that you're waiting for is not machinery, but humans. For example, you can have late. The fraudulent example is one. Is an example here where you can have late data because it needs to be processed by humans first, and in some cases you have deals with your partners that they can come, months or years afterwards. And as I've said before, it's common to solve this with reprocessing. Don't do that. Include it in your workflow graph instead. And in practice, in order to manage this, you need to be explicit that you have 2 time scopes here. So one time scope is the domain time. For March this year, these are the claims that have arrived. For April, these are the claims that have arrived. And the other time domain is the ingestion time, which says by October 10th, these are the claims and therefore the conclusions that I drew regarding the events that happened in April this year. This might sometimes be overkill, but if you deal with financial data processing, this might very well be what you end up doing. This requires a bit more skill in terms of workflow orchestration, but the data processing is typically the same. So one other way that time can goof up your workflow patterns and workflow orchestrations is if you have business logic that is dependent on earlier data way back in time. So this happens, for example, if you store a full history of what the user has been up to, or if you have exponential decays of things, then in order to know the state today, you need to look way back in time. It's often expressed by having a dependency on today's data set, on yesterday's data set, so that has to be calculated first, and then you apply a delta and you get today. That is usually fine if the data sets are small. If the data sets are large, if you decide to do a backfill for some reason and compute from the beginning, you will have a very long computation ahead of you. There are a couple of tricks here. This little code here implements a trick where you take strides, where you take month at a time and aggregate, so you can do quicker strides when you're doing the backfill. I show this to some people at King, and they have a different strategy where they do 10 days at a time, and then they take 10 data sets of 10 days, and they have a 100-day data set and so forth, and then they get a hierarchical rebuild of the history. One of the scenarios where you might need this very long history is when forming sessions out of individual events. It's common to do, when you do analytics, to see for how long was the user active for one reason or another. If you're doing media, you usually want the user to be active for long, listen for long, watch for long. If you're doing sales, you want the user to be active for a short time before he can buy your things. But you often care about these sessions. And defining these sessions is not so easy sometimes. You might say that, okay, if there's at most 5 minutes pause between the clicks, that's sort of the same session. And then you look at, if I do batch, what time window do I need? It turns out that you need infinite, right? Because you can infinitely be active. So okay, then you cap the window to some reasonable time, but then you start scratching your head and you come up with counterexamples, and you realize that you still need infinite time according to this definition, because you might have a session that may or may not be a continuation of the previous session at the beginning of your window. So you come up with various counterexamples, and you conclude that there is no way out of this needing infinite time for many business definitions like this. So effectively, what you have to do is you have to make an artificial cap somewhere and say, let's cut all sessions at a certain time. Again, when I showed this to King, they said we cut all sessions at midnight, just to make it easy. And that's usually the most straightforward solution. And these artificially cut sessions is what was the reason for the graph that looked like this. And this took a long time before we saw it, but some analytical person were looking at the numbers and say, we have like a dip at midnight or 2 a.m. in the morning, and I can't see why. And it turned out that we had artificially introduced a cap that was not acceptable in this case, so we needed larger windows of events. But this is very hard to find out afterwards. So, zooming up again a bit away from time. If you're not used to data engineering but want to start delving in these things, these are a bunch of things of general advice. Strive to avoid complexity and scalable systems as much as you can. If you can do without Hadoop clusters, Spark clusters, that is great. Nowadays with the cloud, you usually can. There's a trade-off between the speed of data and the speed of innovation, because streaming and quick applications have a higher overhead in terms of operations, whereas batch can have very low overhead in terms of operations. Strive for slower data if your use cases can accept it. And many of the problems that I've spoken about here can be addressed by strictly applying functional programming principles, but to architecture. Strive for immutability in data sets. Strive for idempotency, processing without harmful side effects, and make your data pipelines reproducible. Don't go out and probe live systems. That's why we dump them to databases and so forth. And the tool you primarily should pick up, the only new tool that you really use, is the workflow orchestrator. That's the key to success. And what you achieve by adopting these paradigms is team parallelization. In the same way as immutability and reproducibility is good for thread parallelization or machine parallelization, immutability in terms of your data inside your organization is good for parallelization among teams, because they can operate and use the data without closely synchronizing with each other. I usually go out and speak to a bunch of people when gathering information in preparation for a presentation like this. In this case, I spoke to Konstantin and Lena. Thank you very much. If you want to learn more about data engineering, at the Skling website, there's a reading list with, 50-ish articles and presentations from various people. There are also my previous presentations out there. And one final thing that has nothing to do with data engineering. Today, technology and what we do has a significant impact on society. This means that everybody in this room has very large impact on the world around us, much larger than most people in the world. And the choices we make each day on which supplier we choose, in particular which cloud supplier or identity supplier, where we're employed and what product we build, make a significant impact. These are examples of something that I care about. You might not care about them. My point is not that you should care about the same things and you should share my values, nor that you should necessarily care at all. My point is that you should actively decide whether you want your choices to have an impact at all. Let nobody else decide that for you implicitly. Don't be a lemming. That's it. Thank you very much.